All right, welcome to lecture 4.1 over angles and radian measure. So congratulations, y'all made it through the first test. And in general, everyone that actually took the test and took it on time, most everyone did really well on it. I was extremely pleased with the grades on that first test. I know a first test can be a little nerve-wracking because you're not quite sure what to expect. But I hope, besides the mistake in the quiz review or the test review, I hope that you found the test review to be thorough and kind of tie up any loose ends that you had about that first material. So now we're going to move into stuff that looks more like what we're going to be dealing with for the rest of the semester. That first unit worth of material was sort of a bridge between the algebra and moving towards thinking trigonometrically. So now we start hitting the ground running with the trigonometry. So, and this first section is kind of basic. It's probably a lot of things you already knew, perhaps maybe except for radian measure and how to calculate with that and really understand it. But hopefully you've looked through it and found it to be not quite so intimidating as it sounds like. All right, we'll move forward. Okay, so the objectives here, we're going to just talk about the parts of an angle, get some vocabulary down so that it doesn't sound like I'm speaking a complete foreign language to you for the rest of the lesson here. We'll, of course, start out with degree because that's what most of us are familiar with a circle, and with angle measure. And then we'll move into radian measure, converting between the two. We'll talk about angles in standard positions, coterminal angles, length of circular arcs, and then we'll do one application problem with linear and angular speed. And I found, if you've looked at the notes, I found a sweet picture online that helped me wrap my brain a little bit more around linear and angular speed, so hopefully it'll help you too. It always feels like it takes an eternity for that slide to change, and I'm just sitting here waiting on it. And it cuts my mic off when I change slides too, so I can't even like talk and entertain y'all while we're waiting. Not that I'm that entertaining anyway, but you know, hurry up and wait is what it feels like. All right, so let's get going on angles. An angle is formed by two rays that have a common endpoint. So I'm sure we're familiar with what a ray is. That is just a one-directional line. So you have an endpoint on one end and then an arrow on the other moving into infinity. So an angle is formed by two rays that have that common endpoint. You can see the picture there. One ray is called the initial side, which is exactly what you would expect it to be. It's the one you start on. And the other is called the terminal side. So terminal just means it ends here. And we have standard position of angles, and then we've got types of angles that can either be positive or negative. So both of these angles off to the right over here are in standard position. And the reason that they are considered to be in standard position is because the vertex is at the origin of a rectangular coordinate system. Its its initial side lies along the positive x-axis. So let me just grab a pen here and get it a little bit thicker than this. So we're looking at the initial side of these angles running along the positive side of the x-axis. So that's why both of these angles are considered to be in standard form. All right, angle A, so we are considering this one angle A. I took this out of the book and apparently I cut off the labels. I think I put them on your pages though. Angle A is considered a positive angle. And now the reason being seems a little bit counterintuitive when you say it, but it's the way we're really used to seeing angles measured. But it's because it's generated by clockwise rotation. Now, angle B is considered negative because it's generated by clockwise rotation. The reason I say that sounds kind of counterintuitive because you would think that if something's counterclockwise, it's backwards, but in actuality, that's considered a positive angle. So you start at the initial side when it's in standard position, and when you move counterclockwise to get to the terminal side of that angle, that's when it's considered a positive angle. And then if we look at B here, we start at the initial side that's in standard position and we move counterclockwise. That one is considered negative. So these are all pretty basic things here. I assume everybody's good, but if not, give me a quick raise of the hand, or yep, you can give me a green check to let me know you're ready to move forward. Great. Okay, so my husband just walked in, so if you start hearing background music or background rock and guitar, that would be he who is doing so. All right. Moving forward, now this is a really weird word. An angle is called quadrantal. And yes, I was sounding that out so that I would spell it correctly. Angle is called quadrantal if its terminal side, so let me mark the terminal side. Now mark terminal in red because that seems to go together. Its terminal side lies on the x-axis or on the y-axis. And, you know, I'm thinking about, you know, oh, I misspelled this, no, I didn't, I'm good, quadrantal. You know, I was thinking about, you know, why would they call that quadrantal? Well, you have the quadrants, obviously, of the Cartesian plane here. And, you know, the axes form those quadrants by splitting that plane into 4 equal pieces, which is a little strange to think about since they're infinite. Like, how can you split infinity? But for our purposes, those axes break the plane into 4 pieces or quadrants. So that's the association that we can make with a quadrantal angle. So its terminal side has to land on one of the axes. It doesn't matter, on x-axis or the y-axis. They're to be considered quadrantal. All right, so measuring angles using degrees. Now, this is something that you've done since you were in elementary school, when we had the old plastic protractors and we'd get them out and measure those angles. We were measuring in degrees. And a complete rotation through the circle is 360 degrees, or we write that 360 with the little O symbol flying in the air to mean degrees. And I feel even kind of silly saying that to y'all because I'm sure y'all have known that for a while, but it's good to refresh yourselves. Interestingly enough, back before we moved to the Gregorian calendar, the calendar had 360 days in it. You know, there was a lot. I do a lot of reading on sacred geometry and things like that, ancient thought about space and perspective, and 360 is a very sacred number when it comes to thinking about, I guess, life and reality. So it's neat that the circle has 360 degrees in it, because 360 shows up a lot of other places besides just geometry. All right. An acute angle measures less than 90 degrees, and here's the silly old way to remember that. I'm sure y'all are all saying it in your head before I'm saying it out loud, but that's such a cute little angle. That's how I was taught to remember that that's the one that's less than 90 degrees. And of course, 90 degrees is where two opposite axes meet. We have a 90-degree angle there. So when it's less than 90 degrees, we have acute little angle, and a right angle measures exactly 90 degrees, and an obtuse angle measures more than 90 degrees. So I'll just get another color and sketch an obtuse angle for you, maybe something like that, starting at the initial. And actually our example of the quadrantal angle here, if you consider it in its positive form, I don't want to make that statement. I don't know that that's considered an obtuse angle. Oh yeah, but less than 180. There we go. So yeah, actually it's not an obtuse angle, because we have this angle here that would be considered acute. So it's got to be more than 90 but less than 180. And then of course a straight angle is considered 180 degrees because it's just a line. If it weren't for the end point of those rays meeting, you wouldn't even know that it was an angle. You would think it was a line. All right, so measuring angles using radians. An angle whose vertex is at the center is called a central angle. Makes sense. The radian measure of any central angle of the circle is the length of the, I'll put arc, intercepted arc. Okay, so intercepted arc meaning, if you'll look down at the bottom right corner here, intercepted by the rays that form the angle. So we can see right here that this would be considered the intercepted arc there. So it's the radian measure of central angle of a circle is the length of the intercepted arc divided by the circle's radius. So let me put this into perspective for you, because I found this to be fascinating. when I was working with this while preparing to give this lecture here, and, you know, really hadn't in the past given it too much thought besides just kind of memorizing formulas. But what that is saying is that if you take the length, oh, and I've got my colors backwards here. Let me do this, least I completely confuse everyone. Let me rewrite that in a different color. We'll write that in, let's see, orange. Orange is a color I haven't used, so we'll say radius here. Okay, so here's what's fascinating to me. When you take the length of that arc and you divide it by the length of the radius of the circle, right there. So when you divide those two lengths, you always get out from that the measure of the angle right here in radians. And I mean, you know, call me a nerd or whatever, but that's just fascinating to me. Almost as fascinating as thinking about pi. Pi, although it is a value, you know, we estimate it at 3.14, pi is given by the circumference of a circle divided by its diameter. It does not matter what circle you do this with. You could take a coffee can and measure around the outside of it and divide that length by the diameter of that circle that's the coffee can or the cylinder, the circle part of the cylinder, and you're always going to come up with pi. And that's actually how I was taught what pi was. We had a lab where we had all these different circles, and we literally had to go measure them and divide them, and we discovered on our own, oh my gosh, this is 3.14, blah, blah, blah. So I just think that how all this fits together is just so cool. All right, so 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of the circle. So one radian here, let's see, the measure of the central angle, so that's in pink over there, of a circle that intercepts an arc equal in length to the radius of the circle. So if you think about that definition, when this green piece is equal to this orange piece here, you get 1 radian. And that should make sense because anything divided by itself is 1. 3 divided by 3 is 1, except for 0, because you can't divide by 0. 3 divided by 3 is 1. Star divided by star is 1. So I'm being silly there, but it's to illustrate that point. So when that arc length and the radius are equal, we get 1 radian. Everybody cool? Yeah, Roy, you still with us? Yay, all right. All right, I'll move forward. Okay, so computing the measure of an angle in radians. So I'm given some information about a particular angle here, angle theta. That's what this this Greek symbol here is theta. You can just draw a circle with a line through it, and I'll know exactly what you mean. So you're told, and anytime you can draw a picture of something to help you visualize, it's always a good idea. So I have this circle. Use your imagination. So I have this circle with a radius of 12 feet. Okay? And 12 feet intercepts an arc of length 42. So the angle that I want to talk about intercepts the arc, and the arc is 42 feet. And we want to know what is the measurement in radians of theta. So if this little angle is theta here, we want to know what's the measurement in radians of theta. So theta equals, well, we just have to go to our formula that we were given. We were just told that when you divide the arc length by the radius, you get the angle measure in radians. So I have a 42-foot arc divided by a 12-foot radius. Feet divided by feet divides out there, so I don't have to worry about that. And when I divide 42 by 12, I end up getting 3.5. And now I can say that's 3.5 radians. And when I was working through this problem earlier, it just kind of jumped out at me that I may need to point out. That means, because remember, if your arc length is equal to your radius, you've got 1 radian. So basically, our arc length is 3.5 times bigger than our radius. So that's not part of the problem, but I just thought I'd point that out to you, just to help you think about it a little more. Okay, so this is that formula we were just using there. So we have arc length divided by the radius, and that's that intercepted arc length there. And now we want to move to, okay, so how do we actually get to this relationship between radians and degrees? And here's what I came up with. The formula for the circumference of a circle is 2 pi r. 2 times pi times the radius. So if I had an angle that was a full circle, I would have that angle measure is equal to 2 pi r, because my arc length is going to go all the way around the circle, and then I divide that by the radius. Well, my radii divide out there, and I'm left with the circle is 2 pi radians. And I know that there are 360 degrees in a circle. So now that I know that a circle is 2 pi radians, I can say that 2 pi radians is equal to 360 degrees. If I divide that 2 off of both sides, I get that pi radians is equal to 180 degrees. So I know your book just kind of jumps to this right here, but that's the background work, where that came from. Remember, nothing in math is magic. It's all based on principles that have been studied for eons. We call them theorems, and then we have postulates and things like that, proofs, shown by proof. You start out with a postulate and turn it into a theorem by proving it. So that's where that pi radians equals 180 degrees. Now let me just remind you what that looks like on your circle. You're talking about an angle that is straight. So this is my 180 degree angle, and I know now that the measurement of that angle is pi radians, which means the 90 degree angle here would be 1/2 pi radian, because it's half of that straight angle. And we'll go further into all of that in just a moment. Okay, so to convert from degrees to radians, you're going to multiply your degrees by pi radians over 180, and this is all from up here. You can play around with it if you'd like. And then to go from radians to degrees, you're going to multiply by 180 over pi radians. Y'all ready to move forward and actually do some calculating? Roy says yes. Jessica says yes. Madison says yes. Okay, so I have a few for y'all to work on. If you want to go ahead and play around with it while I'm working through it, I would love it if you'd give me the answers to these if you want to participate a little bit. So I'll do this first one with you and then see if you can beat me and give me some of the answers to the other ones. All right, so we're going from degrees to radians here. And so we're told to go from degree to radian. We multiply the degrees by pi radians over 180. And I put that in parentheses so you multiply by that. So we have 30 times pi radians over 180. And I'll show you the simplification here. 30 goes into 30 once and into 180 6 times. And so a 30 degree angle is equivalent to, a 30 degree angle is equivalent to pi over 6 radians. All right. Roy's typing something. I bet it's the answer to the next one. Pi over 6 radians. He got it too. Yay. I thought you were going to type the next one in, Roy. I saw you start typing. Okay, so I'm going to go ahead with the next one and we'll see if Roy beats me. 90 times pi radians over 180. 90 goes into 90 once and into 180 twice. And so when we multiply through, we end up with pi over 2 radians. So that is, there we go, equal to 90 degrees. Ladies, feel free to jump in there. Don't let Roy steal the show here. I'm just kidding. Okay, so last one, negative 135 times pi radians over 180. And when we divide 45 out of each of these, 45 goes into negative 135 negative 3 times and goes into 180 4 times. So we end up with negative 3 pi over 4 radians. Madison, yay! Nice. All right, we're going to go the opposite way, so I'll just remind you to go from radians to degrees. We want to multiply the radians by just the opposite, 180 degrees over pi. All right. Well, pi radians, and they'll divide out. All right, so I start out with pi over 3 radians. I'm sorry, yeah, pi over 3 radians, and which is the same thing as pi radians over 3. Pardon me. Let me show you how that's the same thing real quick. Pi over 3 times radians. That's really radians over 1. I multiply fractions straight across, so that's the same thing as pi radians over 3. So I'm writing it in this way so you can see how it divides out. And I multiply that by 180 degrees over pi radians. And here we get pi radians divided by pi radians. And then, yep, that's it, Roy. And then I have 180 degrees divided by 3, which leaves me with 60 degrees. Perfect. All right, we'll move forward. Here we have 5 pi radians over 3, and we multiply with 180 degrees over pi radians. And divide this out. So pi radians divided by pi radians. And I get 3 goes into 3 one time and into 180 60 times. So perfect, Roy. 300 degrees there. 5 times 60 degrees is 300 degrees. Now, this last one's a little trickier. If I have 1 radian, you have to remember that 1 radian is what you get when your arc length and your radius are equal to each other. And I need to have the pi radians in there somewhere so that they will divide out. So here's how I figured it. Well, if I need the pi in there, I gotta have the pi radians in my numerator. And the only thing that I can divide pi by and get 1 is pi. That's why I did the star over star for you earlier. Because anything divided by itself except for 0 is 1. And I'm gonna multiply that by the 180 degrees over pi radians. And now I get that pi radians and pi radians divide out. And I have, 180 degrees divided by pi. But I'm supposed to just have a number in degrees, some number of degrees. Well, don't forget, pi is a value. It's not 1. But thank you for playing, Roy. I appreciate it. You divide 180 literally by pi. Don't estimate to 3.14 because your graphing calculators have a pi key on them. They're off to the right-hand side of your calculator. I believe it's a second function on your calculator. Yes, ma'am, Madison, that's what I got. And I estimated to the 10th of a degree, so I get approximately 57.3 degrees there. Roy, do you see how that one works out with your pi key there? Excellent. Thumbs up, says Roy. All right, if these make sense to you and y'all are ready to move forward, go ahead and give me your green check to let me know. 1, 2, and I'm certain Madison's ready because she gave the answer to the last one and she is. Clear those out and move forward. Can you hand me my water from my bedside table, please? Okay, so we're just going to dive a little bit deeper into revolving around through an entire circle here of some of the more common angles that you see show up. Let me get a sip of water here. Okay, so the first part of this slide is really just a visual thing. This first one shows you that one revolution is 2 pi radians. And that should make sense because we just figured out that the straight angle, which would be right there, is pi radians. So if you double that, you have 2 pi radians, which is one complete revolution through the circle. So a 360-degree angle, basically, is what that is. And then we have 3/4 of a revolution. So we have, there's half pi right there, radians. And then we have 1 pi radians, pardon me. And then we go to 1 1/2. Well, another way to write 1 1/2 is 3 halves. And notice that is 3 pi over 2 radians. And here's the radian, the 1 radian. So remember, since that, I'm sorry, that's not 1 radian, it's pi radians. So we had half, and then the full there, that straight angle is pi radians. And then we have the 1/4 of the revolution, so the right angle is equivalent to 1/2 pi radians. So pi over 2 radians. All right, let me point this out before I set y'all loose on those problems below. They had these circles quartered up. Let me get my blue pen and quarter up this last one. So we have the 1/4 revolutions through the circle. And then it's also, and there are a lot of them that are important, but this next exercise is going to have you thinking about perhaps going eighths of revolution. So it's just halving those quarters one more time. All right, so notice that some of them are positive and some of them are negative. That is simply direction from your initial side. Your initial side, once again, is always going to be that side. When it's in standard position, it's going to be that side that goes along the positive x-axis. So there are all of the standard, the initial sides to the angles we're going to draw here. Okay, so we have this angle that's given to us as negative pi over 4 radians. And we've got to do a little bit of figuring to see where that actually lands. So let me show you the background work that I did with these. First, I took the absolute value of it because I know it's negative. I know it's going to start and then move clockwise to form the angle. So I really, when I'm doing my calculation to see how much of a revolution I need to move, I don't need to work with the positive and the negative. That's just going to tell me what direction I move once I figure out how far to go around the circle. So I have that, so I'm going to take the positive of it. Pi over 4 has to be equal to something multiplied by, so that's a variable that I'm giving you there, something multiplied by 2 pi. Now let me tell you why I set this up this way. 2 pi is an entire revolution around the circle. And I'm trying to figure out how much pi over 4 is in terms of revolving around the circle. So I need to know what I would have to, what factor I would multiply 2 pi by to tell me how far around the circle I need to go. So that's what that variable x is standing for there, is the amount of the circle. So let me get my pen back here. This is standing for the amount of the full circle. Whenever you have of in mathematics, that's multiplication 9 times out of 10 you're talking about there. So I'm trying to figure out pi over 4 is how much of the full circle. So that's why I set that up that way. And now I simply just do a little bit of algebra here, some simplification. So I want to get that 2 and that pi off of the x so I can see how much of a revolution I need to go. Well, normally I just divide 2 pi off of both sides, but since there's a fraction on the left-hand side, I don't want to divide, because you never divide with fractions, you multiply by the reciprocal. So I'm going to multiply both sides by 1 over 2 pi, that reciprocal that I'm trying to get rid of on the right-hand side. And so I have here 2 pi divided by 2 pi, so now all I have on the right-hand side is x. And so I get x is equal to, well, on the left-hand side, pi divided by pi goes away. So I have a 1 in the numerator and a 2 times 4 in the denominator. So I found out that pi over 4, or negative pi, an angle of negative pi over 4 radians, is equivalent to 1/8 of a revolution backwards, basically, or clockwise around the circle. Well, that's exactly why I cut this circle up here into 8 pieces. So you can see 1/8 of a revolution is going to take you to that negative 45-degree angle there. So if I were going to draw this angle, I'd cut that, I guess the 4th quadrant, if you will, in half with the ray. And I don't have room to put it in here. I guess I do. You really should label your angles. That's a theta. It's not a blob, I promise. So see if you can work ahead of me. You're going to do the same calculation for each of them. The only reason you need the positive and the negative is to tell you what direction to make that amount of revolutions in. So see if you can work ahead of me and get these before I can get them up on the screen here. So here I have 3 pi over 4 is equal to what times 2 pi? 3/8? Actually, you shouldn't have laughed out loud. You got it right, Madison. That's awesome. That's a happy laugh that I just gave. So I'm going to get rid of that 2 pi on both sides. These divide out, so I'm just left with x on the right-hand side. My pi's divide out on the other side as well. And I get 3 over 8. So I need 3/8 of a, that's a bad equal sign. That doesn't even look like an equal sign. So I need 3/8 of a revolution in the positive direction. So halfway between the x-axis and the y-axis is 1/8 of a revolution. I'll dot it for you there. And then I have 2/8 and 3/8 right there. So let me go ahead and bold that in. So this angle here is alpha. Very good, Madison. Excelente. And hopefully Jessica and Roy, y'all got that too. All right, so angle beta is the next one. Once again, you don't need the negative except for when you go to draw it. So 7 pi over 4 equals something times 2 pi. And I'm going to multiply by 1 over 2 pi on both sides. And those divide out, of course. I see that, Roy. All right, yes, 7/8. So I'm going in the negative direction, 7/8. That puts me, I start here, and I go all the way there. So that is angle beta. All right, the last one. 13 pi over 4 is equal to something times that full circle. Multiply by 1 over 2 pi on both sides. Divide out my pi's. Jessica's back with us. All right. And so I get that x equals 13/8. It might be easiest to think of that as a mixed number. That translates to 1 5/8, and I'm going in the positive direction. So this is what this looks like. I make an entire revolution. That's the 1, and then I go 5 more 8. So 1, 2, 3, 4, 5. Here's my angle. And the swirly lets you know that that's a positive angle there. So this is angle gamma. All right, how is that for everybody? Oh, we don't have Jessica anymore. How is that, Roy and Madison? Madison says check, and Roy says I'm typing something. Much better. Oh, good, you had already looked at this. I'm glad it's making sense. Okay, so this particular slide, we don't have any work to do on it. I included this in your notes because it's a really good reference point to have. This is one of those pages that you will want sitting in front of you when you take this test. And this is one of those pages that you may want to copy on that 8.5 by 11 sheet that you're allowed to take into your midterm with you. Now, you can derive any of this. You can do all the figuring, all the calculation, but these are some of the most common angles used throughout trigonometry. So it's just a good idea to either, if you really want to take the time, memorize it, but at the very least, a good page to have in front of you when you're working with circles, angles, even triangles. This comes into big time play when we start talking about triangle trigonometry. So I just put this in there for a reference page. Does anybody have any questions about what you're looking at here? Oh, I forgot to label it. This might help. This is the revolutions, that column. The second column is the revolutions in radians, so the equivalent radians, and then the equivalent degrees for some of the most commonly used angle sizes. So do either of y'all have any questions, or are you ready to move on? We only have a few slides left. Okay, great. Okay, so this page is pretty interesting. I actually, these pictures that I have on here are not out of your book. I went online and looked for some things that could help me wrap my brain around it a little bit better, and found these and found them to be quite helpful. So hopefully you'll find them to be the same. Okay, so let's fill in the blanks here. Two angles with the same initial. Oops, somebody's trying to call. My brother. Let me turn it down there. All right, two angles with the same initial and terminal sides, but possibly different rotations, are called coterminal angles. So they end with each other. That's me just breaking down the pieces of the word coterminal. Co means with, terminal ending. So coterminal, they end with each other. So here's what this, I think this first picture, especially being in color, does an excellent job of showing what coterminal angles are. So I'll just label it here for you. If this is angle alpha there in pink, then angle alpha is coterminal with angle beta there in blue, because they have the same initial side. So I'll do the initial here in orange, my initials in orange, and then they have the same terminal side. They just had different rotations. So hopefully coterminal makes sense to you. Now, when you're increasing or decreasing the degree measure of an angle in center position by an integer multiple of 360. Okay, so let me describe what the integer multiple of 360 means. That means some amount of full rotations around the circle. So if I increase, let's see, if I increase a degree measure by some amount of rotations around the circle, the result is the coterminal angle, and that looks terrible with all the green swirlies on it, so I'll take that off there. But I mean, that's pretty straightforward, so hopefully that makes sense. So thus, an angle of theta degrees is coterminal with an angle of theta plus or minus 360 degrees K, where K is some integer. So say I wanted to go twice around the circle, K would be 2, which means I would actually be adding or subtracting 720 degrees. So that's twice around the circle there. And then increasing or decreasing the radian measure by positive or negative 2 pi k. Since 2 pi is all the way around the circle, 2 pi k plus or minus is going to give you that coterminal angle. So let's work with that. These are easiest seen if you just kind of jump in and work with the calculation. All right, let me move my pen out of the way, or pen pad here, and get my black pen. So assume that these angles are in standard position, and we want to find a positive angle less than 360 that is coterminal with each of the following angles here. Okay, so once around the circle is 360 degrees. Twice around the circle is 720 degrees. So 400 degrees lies somewhere between once and twice around the circle. And I'm wanting to find a positive angle less than 360 degrees. So to do so, I'm going to subtract my K, that 360K, and in this case, my K value is just 1. Because I just want to subtract one whole revolution away from that. I can't subtract 2, or that's going to put me at a negative angle. And I want to end up with a positive angle less than 360. So 400 degrees minus 360 degrees gives me the coterminal angle of 40 degrees. And if we looked at that in a circle, so I'll just draw my origin, or my axes here. The 400 degree angle is roughly, let's see, 360, and then 40 is probably about right there, 40 more. So here is a 400 degree angle, and all that's saying is the coterminal angle to that is 40 degrees. So it starts and stops in the same place. Does that make a little more sense now about the coterminal angles? Give me a check if that makes sense. Roy says yes. Madison says yes. Excellent. Y'all are wonderful. Not that you wouldn't be wonderful if you didn't understand it. I appreciate y'all letting me know, though, because if you didn't understand it, I would definitely want to go into more detail about it. So let me just get this off of here so I have room to work with the other one. So if you want to skip ahead and beat me to the punch here, go for it. I'm going to go ahead and do this next one. Now notice this is a negative 135 degree angle. Once again, I'm trying to end up with a positive angle that's less than 360. So I need to add 360, and Madison says 225, and I'm looking at my notes, Madison, and you are correct. So, and Roy verifies, so negative 135 degrees plus my K is 1 here again, 360 degrees gives me 225 degrees. Beautiful. Okay, so the only difference in working, with radians is that you have to, well, you do have to work in fractions, and to most students, fractions is an F word. But you're going to be adding or subtracting 2 pi multiplied with some value, some integer of K. Yes, you add or subtract 2 pi for that, Madison. Very good. Okay, so 13 pi over 5. Well, first we need to think about what the heck is 13 over 5 pi, so that I can figure out if I need to add or subtract 2 pi over. And yes, you're right, Lloyd. Very good. So this is more than 2 revolutions through, I'm sorry, this is more than 2 pi, because 13 divided by 5 is 2, and then I have 2 3/5. So I'm going to subtract K times 2 pi, and in the case, there's only 1 2 pi in there, because it's 2 3/5 pi, which is 13/5 pi. So I'm just going to subtract 2 pi, but I cannot subtract fractions that do not have a common denominator. So this is really over 1. To get that as a denominator of 5, I feel like we aren't giving her the satisfaction of explaining. Oh, no, y'all are good. I'm going to explain them whether y'all answer them or not. I'm just glad y'all are participating. It makes it so much nicer to have people in here and actually doing the work, and you learn it better that way. I tell my students in my face-to-face classes all the time, don't just sit out there and watch me do it. You're not going to know that you can do it until you actually put your pen or your pencil on the paper and try it yourself. So I build in a lot of group work and just time for them to work on problems. So I'm actually a little bit of a fish out of water in the online version of my lecture because I'm used to just kind of stopping for a moment and saying, okay, go knock yourselves out with these problems and then we'll come back. So I'm glad y'all are participating even though it steals my thunder. Okay, so a little bit about fractions. You have to have a common denominator to subtract or add fractions. And the only way to create that common denominator is through multiplication. And the only thing that's legal to multiply by and not fundamentally change something is 1. So we multiply by this clever form of 1 that is 5 over 5 that gives us the denominator we're looking for. So now I have 13 pi over 5 minus 10 pi, because you multiply fractions straight across, over 5. 13 minus 10 is 3, so I end up with 3 pi over 5, just like Madison did. All right, and this next one, I'm going to be adding 2 pi to get it back into the positive range. So I have negative pi over 15 plus 2 pi, because that's not even a full revolution, that negative pi over 15. So I can just add 2 pi and come out on the positive side, but less than 360. Once again, I need to create that common denominator. So this is really over 1. I'm going to multiply by 15 over 15. And that gives me negative understood 1 pi over 15 plus 30 pi over 15. So negative 1, positive 30, I end up with 29 pi over 15. And that is not bigger than 360 because 29/15 is equivalent to 1 14/15. It's almost a complete revolution, but not quite. Was that one okay for y'all? Okay, good. Let's look at this. Whoa, stray marks. Let's look at this checkpoint exercise here. So we have an 855-degree angle, and we're trying to get a positive angle less than 360 or 2 pi that is coterminal. So we're doing the same types of things, but this time we're going to have to use a larger factor of K than just 1. We used 1 and all the ones above, and this one you got to think a little bit more about. So 855 degrees is bigger than 2 revolutions around the circle. Remember, 1 revolution is 360, 2 revolutions is 720. I don't make 3 revolutions before I go past 855. So the K that I need to use here is 2. And I'm going to subtract to get less than 360. So 855 degrees minus, that's a minus, 2 times 360 degrees. So that's 855 degrees minus 720 degrees gives me 135 degrees. So these you just have to think a little bit more on. Okay, where am I landing if I have an 855 degree angle? All right, so 17 pi over 3. Well, 17 pi over 3 is equivalent to 5 2/3 pi. So before we jump into this, think about it. 2 pi is 1 revolution. 4 pi would be 2 revolutions. 6 pi is 3. So 5 2/3 pi lies between 4 pi and 6 pi. So I'm going to obviously subtract to get myself back down to a positive angle less than 2 pi. I start out with 17 pi over 3, and I'm going to subtract 2, there's my k value, times 2 pi. So that's 17 pi over 3 minus 4 pi, and that's 4 pi over 1. I need to get my common denominator, so my magical form of number 1 of the number 1 there with 3 over 3. So that's 17 pi over 3 minus 12 pi over 3, and I finally end up with 5 pi over 3. So not quite a full revolution. Remember, the full revolution is 2 pi, and if I have 5 pi over 3, then I've got 1 2/3, so I'm 1/3 shy of being 1 full revolution. Sorry, I'm having to tell somebody I'm giving a lecture right now. All right, so this last one, negative 25/6 pi. Negative 25/6 pi is equivalent to negative 4 1/6 pi. Once again, 4 pi is 2 full revolutions, but 4 pi, if I add that back on, won't get us back into the positive because I'm at negative 4 1/6. So for this one, I start out with negative 25 pi over 6, and I need to add, my k is going to be 3. I need to add 3 full revolutions to get back into the positive side. So that's negative 25 pi over 6 plus 6 pi over 1. And I need the 6 in the denominator, so 6 over 6 is what I'm going to multiply by. Negative 25 pi over 6 plus 36 pi over 6 lands me at 11 pi over 6. So that's 1/6 pi short of being 1 full revolution. Y'all good? Roy says yes. Madison says yes. Libby says I'm going to get a drink of water and change the slide. All right. 2 slides left, so bear with me if you will. All right, so just as a reminder, we found out at the beginning that the angle theta is given by the arc length divided by the radius. And now we're trying to figure out, well, how do I calculate the arc length? It's super simple. My arc length is located right here. And if I don't have that and I want it, all I have to do is rearrange this formula to solve for S. So to solve for S in this formula, I'm going to multiply both sides by R. And that gives me, those divide out there, so I get the arc length equals R times theta. So big, tough derivation of a formula there. Nice and neat, hopefully easy to understand. So this is how you get the arc length, is you simply multiply the angle measurement by the radius. So we're given an example here. We have a circle. Once again, use your imagination on my circles. And the circle has a radius of length 6. And we're told that the arc, the intercepted arc by the central angle is 45 degrees. So let me draw the angle here. So that's 45 degrees. And we're trying to figure out what the arc length is. All right. So the issue here is that this particular formula is for radians. And, well, the angle measurement is in radians. And we're given degrees. So that's the first part of this problem that we have to work with, is we need to convert 45 degrees to radians. So 45 degrees times what we learned a few slides ago, pi radians over 180 degrees. Well, my degrees divide out, so those go away. And 45 goes into 45 once, and it goes into 180 4 times. And I end up with the fact that 45 degrees is equivalent to pi over 4 radians. So now I'm going to say my angle theta is equal to pi over 4 radians. Now I'm ready to use the formula that I was given. So I have the formula. Let me get back to my black pen here. I have my formula. Arc length equals radius times theta. So my arc length is 6 times pi over 4 radians. And that gives me 6 pi over 4 radians, which is equivalent to 3 pi over 2 radians. And when I put 3 pi over 2, I'm sorry, we're not talking about radians here. We're talking about inches at this point because we're talking about length. My bad. So when I put this into my calculator, I get that S is approximately 4.71 inches. Y'all good? Roy says yes. Madison says yes. We will move on to the last slide. Okay, so in the last slide's kind of a doozy, just with wrapping your brain around it. At least it took me a minute, and like I said, I was so thankful to find this picture of linear speed and angular speed because it just kind of put things into perspective for me. So if a point is in motion, so consider, let me give this a different color than what they're showing the angular speed as, so this pink point here. This pink point is in motion along a circular path of radius r. So we have our radius here, and that's r. So they've got that measured out to that for you. Through an angle of theta radians in time t, then its linear speed is given by this formula here. So that says linear speed is equal to, well, S is its arc length. You can see right in the wording below that it tells you, okay, that S is that same S we were just dealing with, the arc length that's given by the radius times theta. And its angular speed is given by, well, we use this crazy W looking symbol, and honestly I cannot remember the name of that symbol. So Roy or Madison, if y'all remember what that symbol is called in Greek letters, please chime in and let me know. Maybe we can ask the Google in a minute and see what it says. So we get that the angular speed here with the funny looking W is equal to theta over your time. And the linear, so we have linear speed when we work with all these formulas together. V of a point, a distance r from the center of rotation, it's given by this formula here. V equals r times funny looking W. So where funny looking W is the angular speed from the formula above. So that last formula is kind of putting all the formulas that you see above together. All right, so long before iPods, that holds thousands of songs and plays them with, I don't know if I would say iPods play with superb audio quality, but that's what the book says. So individual songs were delivered on 75 RPMs and 45 RPMs. That stands for revolutions per minute there. I am old enough to have owned a record player and had both 45s and 75s. And I also had a cassette tape player when they first came out in boom boxes and thought it was really cool. Okay, so a 45 RPM record has an angular speed of 45 revolutions per minute. We're asked to find the linear speed in inches per minute at the point where the needle is, oh, you have vinyls? Oh, cool. You have a player still. That's awesome. Do you have a big collection, Roy? Working on it now. Very cool. Yeah, the popularity of vinyl has definitely surged in the past few years, I'd say, or maybe over the past decade. I think people are tired of the what you lose in the digital form of songs. We have a bunch of vinyls in our basement but no player. You should dust them off. You could get a player for next to nothing at like a thrift store, I'm sure. And actually, they're making record players again. So it would be worth it just for the nostalgia of it to find a player to listen to them on. All right, so we have the angular speed at 45 revolutions per minute, and we're trying to find the linear speed in inches per minute. And the point where the needle is 1.5 inches from the record center. So we have the angular speed, funny looking W, is equal to 45 revolutions every 1 minute. And we want to multiply that by 2 pi radians. So I'm just converting here. 2 pi radians every 1 revolution. And that equals out to, well, 45 times 2 is obviously, that's 90 pi radians for every 1 minute, because your revolutions divide out there. So we get that the angular speed is 90 pi radians every 1 minute. And if you think about it, 2 radians is 1 full rotation. So it should make sense that if you divide that 90 by 2, you get 45 rotations or revolutions per minute. So we can go backwards through that as well. All right, now let's focus on the linear speed. So we have that linear speed is equal to the radius times the angular speed. Our radius is 1.5 inches. We're told right here that that's where your needle is sitting on your record. And we're going to multiply that by our angular speed of 90 pi radians per 1 minute, for every 1 minute. And I get here, so 1.5 times 90 is 135 pi inches every 1 minute. And I'm sorry, pi radians. So, oh my goodness, I just did some math magic on my paper and didn't write how I got that. I'm getting, maybe y'all can help me remember what I did here. I'm getting that's 424 inches per minute. Now, how in the heck did I get that? Let me look back in my 135 pi. Oh, geez. Thank you, Roy. Derp. I'm calling temporary insanity on that. Thank you. All right, that's all I have for y'all. I don't even have an ending slide because I was furiously trying to get these onto a PowerPoint before I joined the room. So the next lecture is tomorrow afternoon, so that I don't have brain farts like I just had there through the entire lecture like I did in the 7 a.m. lecture last week. So I will see y'all, if you can make it, at 3 p.m. tomorrow for section 4.2. Thank y'all so much for joining me tonight. You do the same, Madison. I appreciate it. Thanks, Roy. You have a great night, too.